How you doing, guys? In this video we're going to have a look at integration using substitution, and these particular substitutes are used when we see square roots of particular expressions, and we're going to have a look at exactly what we need to substitute to make the integration a little easier. This is a particular way to substitute these trig expressions into the square root functions. This is not the only way you can integrate this, but it is a very nice, simple method so we can integrate particular expressions that involve square roots. Now, this particular one is a semicircle. We haven't been able to integrate or find the area underneath a semicircle before. We do know the area of a circle is pi r squared, so if the limits were quite nice, we could use that particular formula. However, if we want to work out the area between two values that don't sit quite nicely on the graph, well, this is going to be a nice method we can use. So whenever we have something squared plus x squared, we use the tan substitution. When we have the difference and the numbers at the front, we can either use the sine or cosine. And when we have the x squared at the beginning and then we have a subtraction, we're going to use a sec theta. Okay, so here we have the integral of a squared on x squared on your denominator with the square root. So if we can remember what we substitute, that's going to be the tan. So dx d theta is going to be equal to a tan theta, and then when you cross multiply, we end up getting our expression for dx. So when we see dx, we replace a sec squared theta d theta. That's why it's up on your numerator. And on your denominator, we have a squared plus the x value squared. Now, your denominator here is the square root of a squared brackets 1 plus tan squared. And remember our trig identities, sine squared theta plus cos squared theta is equal to 1. If we wanted the one with the 1 plus tan squared, we know tan is sine over cos, so if we divide everything by cos squared theta, we end up getting tan squared theta plus 1 is equal to sec squared theta. So now this expression here is equal to sec squared theta. So your denominator is a squared brackets sec squared, and your denominator is now the square root of a squared sec squared theta, which is just a sec theta. And what we'll notice is the a on the top and the a on the bottom cancel, and the sec theta on the bottom cancels with one of the sec thetas on your numerator. And we looked at this integral of sec theta in one of our first lessons of integration, and it was that really strange expression where we multiply top and bottom by sec theta plus tan theta, something that isn't quite obvious, but then your denominator becomes a function, numerator becomes a derivative, so we end up getting the logarithm of sec theta plus tan theta. But if you notice that the question is in terms of x, our answer is in terms of theta, we need to go back and replace our thetas with our x's. And what we do is look at this, draw a right angle triangle, and notice that tan theta is equal to x over a. So if we have a look at tan theta being opposite over adjacent, if we draw up a right angle triangle and in the position of theta, if we have a look at the opposite side, we write an x, and the adjacent side, we put in an a. When we do that, we can then calculate what the hypotenuse is, and we need the hypotenuse because we end up getting this sec theta, which is 1 over cos. So sec theta, cos is adjacent over hypotenuse, so we need to find out what the inverse is, hypotenuse over adjacent. And our hypotenuse is, using Pythagoras' theorem, the square root of a squared on x squared, and our adjacent is going to be the value of a. So we substitute our sec theta and our tan theta, get a common denominator, and what will happen is we end up getting log to the base e of a squared plus x squared plus x, and then all over a means we subtract the logarithm of the base e of a, and then we have a plus c. Now this part is just a constant value. So see this and this, they're both numerical values, so if we bring them together, it's just another constant, so plus C1. It's a different constant, so let's just denote it as a different constant. So C1 will be sufficient. So there's our answer. Using substitution, looking at the particular expression, is it going to be the tan, is it going to be sine or cos, or is it going to be sec? And that all depends on how the expression looks at the beginning. All right, the next example, I probably wouldn't use substitution. You can sort of see a derivative on top. It's negative 2x, it should be. You can replace that with a negative 2x, balance it out with a negative a half, and then using your integral of f dashed of x, f of x to the power of n dx. I would probably integrate it in that manner. However, I'm just going to show you that you can use substitution in this question. So a squared take away x squared is your denominator. So then we're going to use either sine or cosine. It doesn't matter because it will work out to be the same. So whatever you're more comfortable with. In this example, we've gone x equals sine theta. So dx is going to be cos theta d theta. So whenever you see a dx, replace it with a cos theta d theta. Your x, replace it with a sine theta. And then your denominator becomes 1 minus sine squared theta. 1 minus sine squared is the same as cos squared. So this cos squared theta, and then you find the square root, is just cos theta. So all of that cos theta cancels with that cos theta, so you're just finding the integral of sine theta. Integral of sine theta d theta is negative cos theta plus your constant, and then it's in terms of x, but we've got an answer in terms of theta, and then we can obviously draw a right angle triangle. X over 1 is equal to sine theta, and x is your opposite. 1 is your hypotenuse. Draw up a right angle triangle, find out your adjacent by using Pythagoras, and then we want cos theta, and cos theta is adjacent over hypotenuse. And don't forget the minus. All right, the next one is a little bit more challenging, and you'll see in a moment why it's a bit more challenging. But we've got the addition of x squared plus your a squared using the tan theta as your substitution. And now we end up getting the a value being root 3 because a squared is 3. So then we have a tan theta, so it's root 3 tan theta. Dx is going to be root 3 times sec squared. And now we just substitute those values into the expression. Root 3 times root 3, because we have those two multiplying each other, that becomes your 3. That can be brought outside the integral. And then we end up getting sec cubed theta. We can rewrite that as sec theta times sec squared theta. And we might want to use integration by parts. Remember, this is 3 outside of uv, take away the integral of v du. Choose your dv to be something that you can integrate, hence why we've got the sec squared. Integrating that, you get tan, and differentiating sec, you differentiate 1 over cos. And 1 over cos, so if u equals cos theta to the negative 1, du dx is going to be equal to, bring out the minus 1 to the front, rewrite cos theta, take away a power, so take away 1, so it's minus 2, multiplied by the derivative of cos, which is negative sine, double negative goes, and then you end up getting sine theta on cos theta times 1 over cos theta, and hence you have your tan theta times your sec theta. That should have been a theta, not an x, sorry. So replacing all those values in your u's and your v sections, you end up getting this expression. Remember that 3 multiplies that whole set of brackets. And just simplifying this somewhat, we end up getting, this is the same as that. Tan squared theta is 1 plus sec squared. Sorry, not 1 plus sec squared. Let me just rewrite that. So we end up getting 1 plus tan squared is equal to sec squared theta. So when we have a sec theta multiplied by sec squared minus 1, we end up getting the expansion right here. So we end up getting negative 3 multiplied by sec theta times sec squared, which is sec cubed, and negative 3 sec theta times negative 1, the double negative turns into a plus. Now we want to integrate sec theta. We saw that in one of the previous questions. We end up getting log of sec theta plus tan theta. And then this, if we just rewrite that, that was actually what the question was. Okay, so just be very mindful of that. So this is the question. This is also the question, just written in a different way. Draw up your right angle triangle because we want to get it back into values of x. So sec theta is equal to 1 over cos, so it's going to be hypotenuse over adjacent. Tan theta is equal to opposite over adjacent, so that's what we got here. Take away 3 lots of sec cubed. So this is the question. So 3 sec cubed is the question. So therefore we can rewrite the question out like this in values of x. And the last part is our substitution of 3 log of sec theta plus tan theta. Getting the, because the question was on both sides, getting it to the other side, you end up getting 2 lots of the integral. And this is what we've got left on the right-hand side. We don't have to do much with our answer, so dividing everything by 2. So if I divide by 2, this becomes over 2, this becomes over 2, and our constant becomes over 2, so let's just write C1. And our final answer can be left without our denominator here, like we have seen in the other question. So I'm going to just call that C1. This is going to be a division of a logarithm. So when you break up a division, you subtract the individual logarithms. So it actually is embedded in the constant. It combines with a constant, so we end up getting, as you can see, another constant. I'm going to call it C2. So this part becomes 3 over 2 outside of natural logarithm of the square root of x squared plus 3 plus an x, take away the natural logarithm of root 3. And the 3 on 2 multiplied by this logarithm has been brought in with that constant, so you don't really need to have that in your expression. So we've just called it C2. So that's why this question was a little bit more challenging, because you got your substitution, but then you need to manipulate your expression so you can bring it to the other side. And that's what we're going to be doing quite a lot with our reduction formula, which is at the end of this topic. So you need to be able to recognize what the question started with, and then see if you can manipulate it to make your integration somewhat nicer. So there you have it. Just remember what values you have to substitute depending on what type of expression that you get. But yeah, there you go. There's integration by trig substitution.